Today our goal is to be able to look at a graph and find the function of the simple harmonic oscillator. Okay, so we're going to do this in a couple of parts. So the first thing we want to do is we want to figure out what is the equilibrium position. So the equilibrium position is sort of this line, this midpoint line that the function oscillates around. So somewhere here in the middle there's a line, and we call that the equilibrium position, and we label it y0. So we got to figure that out. So the easiest way to get that accurately is to find the maximum value of y. So y has some maximum value up here, and we're going to call that y max. And it has some minimum value of y, and of course this could also be x. That's the minimum value of x. And so the idea is that the equilibrium position is halfway between the maximum and the minimum. So if we take the maximum value of y and we add to it the minimum value of y and we divide by 2, that is the equilibrium position. Okay, so in this case, the maximum value of y we can tell from the graph. You can see the graph, the maximum value of y is right here. That's at 5. So from the graph, we can tell the maximum value of y is 5. The minimum value is right here. That's 1. We divide that by 2, and we get 3, which you probably could have figured out by inspection on this graph. But we can, when the numbers or the graphs don't line up so nicely, it's a little harder to tell by inspection. So now we know the equilibrium value of y. Okay? So we call that y naught, and that's 3. Okay, the next thing we want to do is figure out the amplitude of the oscillation. So the amplitude of the oscillation is the maximum displacement from equilibrium. So we call that the amplitude, and this would be the amplitude, and that would be the amplitude. So it's the maximum displacement from equilibrium. So to figure out the amplitude, we can simply take y max and subtract the equilibrium position. In our case, that is 5 minus 3, or 2. And I think, again, that's pretty easy on this graph to tell that the amplitude is 2, because the graph goes from 3, the equilibrium, all the way up to 5, and it goes from 3 down to 1. So we can calculate the amplitude. So what we know so far is the equilibrium position, and we know the amplitude of the oscillation is 3 meters in this case. Okay? All right, so that's going to help us write the function. Now, let's move on. The next thing we need to figure out is the period. Okay? So let's move on, take another look at this graph here. The period is the time it takes to complete a cycle. So this graph here is a cosine. So we're going to write the function y of t equals the amplitude times the cosine of something plus the equilibrium position. Okay? And in here, we put omega times t, where omega is this angular velocity. And the way to figure out omega is that it always equals 2 pi divided by the period. Okay, so we have to find the period in order to write the function, because what goes in here is 2 pi. So if you think about a cosine graph, you know it's cosine because it starts at its maximum value. So the period is the time it takes to go from the maximum value until it is back at the point where it started. So since this is a time axis down here, the period is the time it takes to go from there to there. Okay? And it's a little hard to figure that out from the graph, but we do have a point that we are given. So from here to here is one period, and then we have another period from this max to this max, and another period from this max to this max. And so here, when time equals 15, that is 3 periods. Or maybe it'd be easier to just look and see here after 2 periods, it's on a grid line, it's 10 seconds. So either way, we can figure out that the period is the time it takes to complete a cycle, which happens 2 times in 10 seconds. So the period is 5 seconds. Okay, so we're just going to look at the time domain because what we have here graphed is the time on this axis. So if you could spot this easily, you could probably tell that's between 4 and 6. Maybe it's 5. Maybe it's 5.9. It's a little hard to tell. But since you're given a point for the third period here, you can figure out it's 15 divided by 3 or 5. Okay? All right, so now we know the period. So now we can figure out how to write this function, because that's our goal. Our goal is to write the function. So omega is going to be 2 pi divided by the period, which is 5. And you can figure out a decimal approximation for that, but you don't really need to. So now let's write the equation for this function. Y, the position of the oscillator at any time, is given by the amplitude, which we figured out was 2, times the cosine of the angular velocity, which is 2 pi over 5, times the time, plus the equilibrium position, which is 3. So this is the function that describes the harmonic oscillator. And somehow my thing got filled, so there we go. All right, so that's what we're after, and that's what I'm going to be asking you to do on the problem set. All right? Now, once you have the function, you can do all kinds of things. So, for example, suppose I asked you to tell me what is the position of the oscillator at 8 seconds. So at 8 seconds, we want to know where is this oscillator. So we're thinking about this point right here when t equals 8 seconds, and I want to know where is the oscillator. So I can tell that it's somewhere between 1 and 1.5, but I don't really know very carefully. I need to use the function. So what I can do is I can plug that in. The position of the oscillator at 8 seconds is going to be 2 times the cosine of 2 pi over 5 times the time, which is 8 seconds, plus 3. So you can evaluate this in your calculator, or you can simply graph it on your graphing calculator and go to where t equals 8, and you can find the value of the function at 8. And so for me, I plug that into my Desmos calculator, and I get 1.38. So you can see here I got 1.38. So that agrees with my answer up here because I thought it was somewhere between 1 and 1.5. So it's 1.38. Okay? You could also do things like figure out the velocity. If you want to know what is the velocity at a point, what is the velocity right here, you can find the position right before it and the position right after it. And then you can find the equation of the line from here to here. So you could find the position right before and right after, and then find the slope of the line. And remember, if you're graphing position versus time, the slope of the line is going to give you the velocity. So right here, the slope would be the velocity of the oscillator at this time, which is given by, let's say, right there. Okay, so at that time, t, you go a little bit before, a little bit after, find the position, and then you can find the slope, and that's the velocity. So the goal is to find the function. Okay, so just a quick reminder, if the function starts at its maximum, okay, so it starts at its maximum and then goes down and up and down and up, that's a cosine function. On the other hand, if it starts at the equilibrium position and goes up and then down and then up and then down, so this one started at its equilibrium position, then starting at its equilibrium position tells you that it is a sine function. So in general, we can write the position, y of t, if it's moving vertically, equals a times the sine of omega t plus y naught, or if it starts at its maximum, which is more common, then we can say y of t equals a cosine of omega t plus y naught. So on the AP exam, we're never going to have any left or right shifts. You won't have to worry about adding in a left or right shift. It'll either be a sine or a cosine function. But of course, when you're fitting real data like we did in lab, you have to be able to shift the function. And I should note that this is in the y direction. An oscillator can be attached to a spring, and it can vibrate horizontally, and then, of course, we would say x of t equals a cosine of omega t plus x naught, if it's a horizontal oscillator. All right, so you're going to practice with a problem set. There's a couple of graphs. You're going to have to find the function and then use the function to find the position at a couple places, just kind of like I've done here. So that'll be your job for today, okay?